My name is Burkhard Ringlein. I'm with IBM, and I would like to present the work we did in Zurich around the platform portability. I guess you have seen similar charts throughout the day that model sizes explode, but also not only model sizes explode, also the GPUs get larger, and not only GPUs get larger, they get even more diverse. So we get new hardware, they get larger, we get all kinds of accelerators. You have seen many, many keywords throughout the day. And now the question is, how can we run these large models on this diverse set of hardware, so this heterogeneous hardware? And to show you some numbers for this, because for conferences like Ray Summit or a distinguished crowd like you, I would like to have some numbers on my side. I stole this curve from Hennessy and Patterson from their Turing lecture, how you can achieve 5 orders of magnitude speed up for a simple matrix multiplication by applying well-known optimization methods like loop unrolling and memory tiling and using vector instructions. And even on a somehow stupid CPU, you need to take care of the memory layout in order to achieve good performance. So given that, how can we ensure that all these great models can be executed with the best possible performance on all hardware without re-implementing every model for every cache size, for every GPU generation again? And that's why I would like to take you on a journey to portable and fast LLM inference. And I will start with some background around vLLM and Triton. Then I will introduce you the concept of autotuning, because autotuning is necessary to achieve platform portability. However, autotuning has some problems in practice, and I will tell you how to overcome these problems in practice. And finally, in roughly 23 minutes, I will show you some results. I will demonstrate what I did, and hopefully we arrive together at a conclusion. My goal in this presentation is to sketch you the future of performance and platform portability for large language model inference using vLLM and Triton, and somehow unofficially make you all fans of our introduced framework, Triton dejavu, which I will present later. So, in case you didn't hear and you were the rest of the day somewhere else and not in the vLLM track, vLLM is a state-of-the-art framework for model inference. And the detail that is important for this talk is that the state-of-the-art performance comes from custom model code and low-level optimizations within this custom model code. So in the earlier talk about the state of vLLM, there was a list of all the kernels, say, hand-tuned to get the best performance. Some of them are in PyTorch, some of them are in CUDA. However, if you have hand-tuned, if your performance depends on hand-tuned kernels, then you have, by definition, limited portability. Besides these PyTorch and CUDA kernels, some of the kernels are also written in OpenAI Triton, which I will introduce in a second. And if we look at this architecture, the question comes to mind, how can we ensure that all these hand-tuned kernels achieve the best possible performance on all platforms? And what is this OpenAI Triton? And in this presentation, I will also share with you how to do that. So, next introduction, in case you didn't hear of it, Triton is a domain-specific language developed by a PhD thesis in Harvard. And then the first author joined OpenAI, and they maintained it as open source code. That's why it's called OpenAI Triton, to differentiate from NVIDIA Triton, which is another inference server, so somehow a competitor to vLLM. And I won't talk about that. I will talk always about, and if I mention Triton in this presentation, always about this language, OpenAI Triton. The claim to fame for Triton is that it has competitive or superior performance to hand-tuned and proprietary libraries from NVIDIA, like Q+ or QDNN, but it's purely open source. Its programming model is based around tiles, and it also supports not only NVIDIA, but also other platforms like AMD, Intel, and more experimental platforms coming up. So how can Triton achieve superior performance, but by just being very easy open source optimizations? So Triton has a tile-based programming model. That means the model is, from the programmer point of view, around single program multiple data, so SPMD. So the programmer does not need to program the parallelization itself. I stole here a figure from the Triton paper comparing the CUDA model and the Triton programming model. And if you look at it from some distance, it doesn't look so much different. If you code in CUDA, you usually give each thread its own thing to do. So you need, if you iterate over loops or you have nested loops for very complex matrix multiplication or attention kernels, you need to keep track of your indexes, and then you tell each thread what to do on a CPU. However, for Triton, first, Triton can be programmed in Python, which I personally find is more convenient than CUDA. And secondly, you don't need to define every thread what it needs to be done. You can define ranges. And then these ranges are split. The compiler will split these ranges into each thread, into each shared memory, what they need to do. So it looks like only a slight difference to this between this loop on indexes and these ranges. But apparently, this slight difference allows much easier optimizations of liveness analysis, better memory management follows from that. It's easier to split these nested loops into smaller tiles because you can infer the ranges automatically. And also static scheduling and so on gets easier. And as of today, the Triton documentation still mentions the resulting system works actually surprisingly well. So they are still surprised that this small difference apparently is very important to achieve high performance on processors like GPUs. One footnote to that is that the performance mainly depends on how you split these ranges into smaller blocks. And natively, it is, I guess, easy to imagine that these blocks are then mapped to caches and shared memory and so on, and that the size determines the performance. And Triton allows you to do that. So you code this like a variable, and you are able to define this block size, so how this range should be split at runtime, because Triton is a just-in-time compiler. And for different scenarios, so different models, different GPUs, we need then different configurations of these block size. So that is what configurations for Triton kernels is about. So now we put Triton into vLLM. Simon mentioned already there are a lot of kernels in vLLM using Triton, but none of these kernels use the autotuner. So autotuner is a concept from Triton that allows you to tune these block size I mentioned on the slide before to every different scenario. Usually the Triton kernels in vLLM have hard-coded configurations, so block sizes, or very simple heuristics, or use custom JSON lists to get the assumed best possible performance. The result is that the Triton kernels run well on, for example, an A100 or H100 if the developer tuned it for that, but do not run well on other GPUs. So we again have, in combination with the CUDA kernels, limited portability and limited performance portability. So now this limited performance portability I mentioned already quite some time in this talk, and if you are not in an HPC or computer architecture background, it may be new for you. So what does it mean? It basically says that, well, you can tune your algorithm for one platform, or you developed your algorithm for a specific GPU, but if you run it on a different GPU, it has worse performance. And that is even true for GPUs within the same vendor, so not only between, for example, NVIDIA, AMD, or Intel, but also if you have different NVIDIA generations, the architecture changed a lot, so the performance could decrease. And here's an example of some vLLM kernels, the reshape and cache kernel. And green is, you see in this figure on the x-axis, the size of the array, so for example, batch size times head size and so on. On the y-axis, the latency, lower is better. That is a reshape and cache kernel to prepare the KV cache. Green is a vLLM implementation in CUDA, and in purple is my Triton implementation, which is usually always faster. If we execute the same test bench on an H100, then you notice a gap here, because actually the performance of the CUDA kernel is the same, meaning the CUDA kernel cannot leverage the superior architecture of the Hopper GPU. However, the Triton code can, and the Triton can adapt to this new architecture due to the auto-tuning, because this block sizes and the adaptation of the code to a new architecture is done automatically. So and before we go there into more details, what does this autotuning do in detail? I have the same kernel here again. However, I disabled the autotuning of Triton, and I hard-coded the block sizes. And you see now two curves of Triton. One is a light purple curve that has a large block size, and the dark purple curve has a small block size. And as you can see, for smaller arrays, the smaller block size is superior. For larger arrays, at some point, the larger block size is superior. So that is not unexpected. And if you enable Triton autotuning, then you merge the performance behavior because the autotuner picks for every array size, meaning number of tokens multiplied by batch size, number multiplied by number of heads, and so on, the best possible configuration. And that's why for this kernel, Triton is always better. So looking at that, the solution could be easy, right? We could use Triton autotune everywhere because it's built in the Triton library. And of course, we should write more kernels in Triton. However, the Triton autotuner evaluates all possible configurations sequentially, and that takes some time, or could take some time. And depending on the kernel, depending on the search space of the autotuner, this could take even days. Meaning, if you would use the native Triton autotuning in production, you would to start a new inference server, it could take 3 days or 8 days until this inference server is up and running, which is, of course, prohibitive, so cannot be done within a production system. So now we have the problem. In order to achieve best possible performance on multiple hardware, we need to use autotuning, but autotuning is prohibitive expensive in production. So what can we do? And that is the contributions we in IBM Research did. We developed a framework called Triton dejavu, because our observation was that for a given platform, so a given GPU and a given kernel configuration, the decision of the autotuner could more or less be predicted, because if you multiply a specific matrix on an A100, it will always be the best configuration for this particular GPU. So we thought we'd just teach Triton to have some déjà vu mechanism, so it remember what it did before. We open sourced this framework. It has in the meantime also more stars and forks than on this slide. And we are also in discussion with the Triton community to merge this upstream. So how does this déjà vu mechanism for AI inference can work? The first two phases here, the kernel development is the same, and also then the developer provides a list of configurations that the developer thinks could be good for this kernel. However, then we also add a second list here in the third step and define the use cases, because the tuning decision depends on the shapes of the arrays of the Triton kernel. So we need to define for which models, for which batch size, and so on, these kernels are intended to run. Then in an automatic cache preparation phase, we select for all these defined use cases the best possible configurations across all hardware and save it to a simple JSON file. And then this JSON file can be included in the container, and the container is ready for fast deployment. And of course, all of that could be fully automated and is also gated against changes. So if we want to build a new container, but nothing in the Triton kernel changed, we don't need to run the cache preparation stage again. Why is this safe to use? So why can we be sure that our déjà vu mechanism does not pick the wrong configuration at the wrong time? We did some research in this direction and tried to ensure which criteria we need to know to say, okay, we can use this configuration safely. And we came up with this list. And I guess the first are obvious. We need, of course, the performance, and the selection of the Triton kernel depends on the CUDA version, the PyTorch version, the Triton version itself, and the GPU. Then, of course, it also depends on the code version. So we need to have the hash of the Triton code, of the just-in-time compiled function. Then we need, but only the code. We don't need to have the hash of the libraries or so, because that is actually deployment independent. And of course, we need the hashes of the configurations we think this kernel should be good for, and also the hash of some autotuner parameters, like how long the autotuner should run, because also that influences the autotuner decision. Then the version of our own framework, and the last one is optional, But while developing this framework, I wanted to know which kernel cache file was for which kernel, so I added a human-readable label there, the signature of the function. And this tree of JSON files then can be simply included into the containers as stated before. And since we now have the option to go and can reuse large amounts of Triton configurations, we actually came across that not only we should use a dozen or 20 or 30 configurations for each Triton kernel, but actually for the best possible performance, we need hundreds of configurations. And then it's more efficient to go through these hundreds of configurations with configuration spaces and not lists like Triton is doing it. And we also need some heuristics in case in production we hit a corner case that we did not optimize for. We also added this to our open source library. So the previous figures I showed you were about different generations of GPUs, and now what about performance portability for different vendors? So can we actually execute the same Triton code in AMD and NVIDIA? And the answer is yes, it is possible. I executed on this figure a kernel that was written by AMD's ROC-M team for flash attention. That is the brown curve here on an NVIDIA A100, and compared it to the latest and greatest flash attention package of Tridao. And as you can see, you don't see a lot of difference here on this figure. So sometimes the Triton kernel is actually faster. Some other times the Triton kernel in larger array sizes is slower. But only minor, it's getting close. The y-axis has a logarithmic scale. So if you then look, for example, at the red curve, that is the same Triton code executed, but without my auto-tuning using the AMD configurations on an NVIDIA GPU. So obviously, this configuration runs worse. So we achieve only 70% of possible performance. If you disable auto-tuning altogether, so how Triton is used most of the time, then you end up achieving only 15% of the possible performance, so a 6 to 7% slowdown, 6 to 7x slowdown. And yeah, so bottom line, you can achieve true platform portability with competitive performance with OpenAI Triton. However, you need to use auto-tuning. One last point in this direction. If you also look at the end-to-end performance, I did a evaluating Llama 7 billion model. I did this already in May, so it was before all these Llama 3 models were out. And if you compare Llama 7 billion and in this figure, and on the x-axis you have the throughput, and on the y-axis you have the time to first token, as in similar figures earlier today. The blue curve is vLLM 0.6 as of 2 weeks ago. The purple curve is the same model, but with just Triton kernels, so without any CUDA code involved or PyTorch native code. And the orange curve is the same model with only Triton, but without auto-tuning. And as you can see, that has a huge performance gap of 30%. The Triton-only model gets close with only 8% slower for large batch sizes and for smaller number of users. So the numbers here on the curve are actually the number of users. I should have mentioned that. For a smaller number of users, we are actually faster. And yeah, we did this evaluation with another project. We developed FMPerf. To do this evaluation, I needed to implement a number of Triton kernels, the activations, the reshape and cache I showed you earlier, the layer norm, and then I used the flash attention from AMD. So that was about, okay, we can get with Triton-only models actually close to state-of-the-art performance or even superior, and there's also work of my colleagues done within the PyTorch community around in this direction. So now if we use Triton dejavu, does it actually bring what we need? And here I evaluated the startup time of Llama 7 billion again, and then of a larger model called Maxtral. On the x-axis, you see if you use the upstream Triton native auto-tuning, how long it would take until the container is ready to get requests. And on the second bar is then if you use the same container with Triton dejavu. So yeah, as you can see, it takes ridiculously long for if you use native auto-tuning. For Llama 7 billion, it could take up to 17 hours. For mixed trial, even 8 days, which is, as I said before, prohibitive expensive. And if you look at the numbers here, for an H100 in orange, it takes 8 days or 56 seconds. So then I could claim in theory I have a speed up of 5 orders of magnitude by using our framework Triton dejavu. But I also think this number is a little bit ridiculous because no one would do it in practice like this, right? However, with Triton dejavu, it is possible to do it in practice. So, and to show also that we can not only make nice plots, I want to demonstrate it in a brief video. I did a Triton-only deployment for vLLM. We replaced all the custom CUDA kernels. As I said before, I implemented some of them, and then we demonstrate this in using vLLM, of course. So I hope that works now, but it looks great. So that is a video I did before because I didn't want to bet on any Wi-Fi here in the conference. So here you see I start a Docker container, and I start a bash in this Docker container first because I want to show you how this Triton dejavu cache looks like. So I show you here the folder structure, the folder tree, where you see, okay, that is a cache tuned for CUDA 12.4, A100, and so on. And there are a lot of cache files lying around with a lot of hashes. I can also show you how there are even more cache files lying around. I can show you even also how one of these cache files looks like. If I open the first 10 lines of one of these files, you see there are again all of the hashes I presented before in the file, then the signature, how long it took to get this file, and how many configurations I evaluated, and then for each case, so that is a list of the autotuner key, what is the best configuration. So very simple, actually. And then also to prove I actually use Triton code, that is an activation code I implemented, and there I define the configuration space that Triton dejavu needed to go through earlier if I want to use CUDA graphs and so on. And now I start the OpenAI server. I use enforce eager because we only care about the time to first token. And here you see some log messages and that Triton dejavu actually did get started and found the configurations, and also I added some log messages that we have the Triton kernels up and running. So now that are roughly 30 seconds, the server is up and running. On the right-hand side, I now make a default request with a default OpenAI API and ask about what could I do in San Francisco. And as you see, well, there's no latency, and we can execute again. There's no latency for auto-tuning. And now we also can ask about I like San Francisco, but I would admit I like Zurich more, so let's see what the model says about Zurich. And yeah, that's it. So that is a brief demonstration that we then can use Triton Autotuner to achieve true platform portability and performance portability without any overhead in production. So I hope in this brief talk I could convince you that performance portability is critical to scale to many different scenarios. If you don't have your own data center with your own homogeneous hardware, it's probably you have a lot of different hardware where a server needs to run well, and that also applies to open source frameworks like vLLM. OpenAI Triton is a very interesting domain-specific language, and it's used widely, and it enhances the performance and portability of vLLM kernels. However, we need auto-tuning to achieve the best possible performance and true performance portability, and we need to auto-tune and remember it, otherwise we cannot use it in production. We open sourced the library a couple of weeks ago, and the pull requests to merge that into vLLM are in preparation. However, there's still some work we want to do in this direction. We want to make the fallback heuristic more efficient. We want to use not only sequential search in the autotuner, we may want to use better search algorithms like Bayesian optimization or genetic algorithms. And of course, it's open source, so you can also contribute your ideas. We think that since there will be many, many more hardware coming out in the future, something like performance portability is necessary to making vLLM future-proof, and we hope we contribute into this direction. And now I look forward to all your questions.
Let's thank the speaker. All right, please raise your hand if you have questions. All right, catch up.
Thank you for the great work. I have one question do you have some expected timeline to get it into Triton? I think this should be a fantastic feature of Triton itself, and it's surprising that it's still missing in Triton.
Thank you for this question. It surprises me too. And I was also at the Triton conference 2 weeks ago, and we had a chat with the developers. And yeah, to put it diplomatically, I guess it's not on their priority list. And we can talk about that more offline, off the record, I think.
Another follow-up is that we are integrating torch compile, and the inductor will directly generate these Triton kernels. So if we want to, we need to manually insert like this library.
Yeah.
It's difficult to do that in inductor. So
yes, absolutely. Also, actually, inductor also uses the Triton Autotuner, and we were thinking maybe we just contributed to PyTorch then directly for torch inductor. But yeah, that's another thing we look into.
Yeah, thank you.
I didn't take. I hope Simon takes care of who.
Yeah, it looks great. The question I had is, you have that cache that you generate from the auto-tuning.
Yeah.
Is the idea that vLLM ships with a lot of these caches by default, so people don't have to even worry about that? Like you just.
Yeah.
Because I think everyone building their own image seems a bit like.
Yeah.
Hard.
Oh no. As of right now, there is something similar for the fused MOE kernel already in vLLM, where you have many JSON files for different configurations. And this solution would improve that and also make it more general for other Triton kernels. So yeah, the idea is that many of these JSON files are then part of, one way or the other, the vLLM project.
We have time for more.
I guess there were 2 questions.
The follow-up for the first question, do you have any insight they don't support this feature? How do they run the system in production? It takes 8 days to start up. So you mentioned that this feature is not in the Triton roadmap. So do you have any insight how they run it in production?
I think, thanks for the the question. I think the company that most of the people using Triton in production right now have a very homogeneous setup. So they auto-tune, they tune the kernels manually and then have a default configuration they always take. However, I must also admit, I thought in the beginning I'm smarter than the auto-tuner, and since I did a lot with computer architecture, I can find the best configuration by my gut feeling. However, that is not true. So I was constantly beaten by my own algorithm, finding the better algorithm for a specific platform. So besides that many people do it in production like that, I would advise using auto-tuning and Triton dejavu, even if you think you know what the best configuration is.
Maybe it was already mentioned, but I just want to check. So, for example, you said the config that you want to auto-tune over, and let's say it runs, everything gets cached, and now you want to modify the config to expand it, like to evaluate a wider set of parameters for the auto-tuner. Does it reuse that cache, or?
Yeah. Yes, so that's the idea that with this extensive list of hashes, so that we know exactly what we can reuse and what not, but reuse as much as possible, because at some point compute gets expensive. Yeah, thanks.
We have another question, which is about, for example, in LoRa, in the Punica kernels, they were a couple of weeks ago ported to Triton, right, or a couple of months. So, and they can be loaded separately from the main model, right? So if you have a configuration like that, would you have JSON files for the model and for the LoRa weights, or would it be one single JSON file for both?
It would be, I think you are in the, thanks for your question. I think in the sense of your question, it would be one JSON file for each kernel. If you have then multiple kernels, then it would be multiple JSON file, but if you have one kernel that you use in different scenarios, it's one cache. Because then it also would be just in time compiled by Triton as one kernel. So that's how we merged it there.
Thanks.
Any other questions? All right, let's thank the speaker again. Awesome talk.
Thank you.